Welcome to this video tutorial of how to program 11200 top point XYZ Direct. So basically we're going to be measuring some direct characteristics here, meaning we're going to probe some points on the part and we're simply going to output the X, Y, or Z locations of those points. So I have the blueprint up here. I've already taken the liberty of ballooning this blueprint. I elected to do that in PowerPoint, but of course you can just print this out and do this manually if you like. So we can get rid of this here, and we are going to come into Course Information tab here, and we're going to come down to STCC SOP for creating measurement plans, and this document will guide us through how we should do this. So step one, we're going to import our CAD. So we'll pop over to Calypso, and we will go CAD file, and load. For this, we'll pick cadcube.sat, that is top option there. And then we'll set our interface right here. I can't even see my icons here, so I'll just full screen Calypso, and now we see our icons come in down at the bottom. And I will turn on shading for that CAD model. So our next move is to orient the CAD if necessary. In this case, our CAD is already in the correct orientation. So our next move is going to be to place it on the machine. Now truly, this is optional. I will show this to you. You can certainly try it if you like. If you have any amount of hard time with it, I would skip it for now and ask me how to do this in class. So we do have to open up Calypso Simulation to make this work. We'll resize our windows a little bit, and I'm finding that the best way to do this is to set this pull down to base alignment so we don't need it anymore. And then I like to leave my stoplight window so that the X is just underneath the overall Calypso Windows X. And then I put my measurement plan simulation directly below my XYZ readout because nothing else here is relevant. All right, now within this window, we can click on Modify CAD Model. And we can also click on Display Machine. So Modify CAD Model allows us to move around. Display Machine allows us to see where we are in the machine. And the models will always come in with their origin at the machine's origin. And of course, that's not helpful for us. So ignore everything about this CAD entity window here and click on Position. Click on the bottom of the part, rotate the model, and then click right about here on the table and then hit Apply. So it really is as simple as that. Now you hear collision detection in the background. It thinks that we hit something. So that's what that noise is about. We can actually just turn that collision detection off for right now. We'll close this window. And we no longer need to see the machine at this point. Really, the only reason why we put our part here is if we want to do, what do they call it? If we want to do check measuring range, we do have to be within our measuring range. Now again, this step is optional because if you're not checking your measurement range, usually you wouldn't even turn on the CMM's display at all. You know that your part is small enough to fit inside the machine, so it is not an issue, right? So that step is completely optional in this case. So step 4, select probe. So if your probe is not already selected, we would come over here, and again, ironically, we do the automatic stylus system change when we're in person. We do the manual stylus system change when we are an offline because Calypso doesn't know where your probe changer rack is, so it will throw errors if you try automatic, right? So we do manual stylus system change. We pick up our stylus system. It'll say insert stylus system. You're going to pick 3 by 50 millimeter stylus from the list, and then say OK and close. Now I already had that in position. If you didn't already have that probe active, then you would see the probe would change right now. So we selected our probe. Our next move is base alignment. So we'll come over here to base alignment. We'll say OK to the default menu. And I've started to just rename this here. I rename it Auto Align. Right, so I just name it Auto Align, and that way I only get 3 base alignments in my list, or alignment selections, I should say, when you do the run dialog. And I'll tell you a little bit more about what I mean here when we're in class. So here the base alignment window is open. It looks like we should do something, and I think it's this could be more obvious than it is. We come down here to define select geometry, right? So this kind of makes it look like you should be clicking something up here. You should not be. You come down here to define select geometry, and then we'll click right on the plane on the top surface. Then we'll hit the pull down, define line on plane. We will click and hold the mouse and then let go. And notice that this is populating as we go, this alignment window. Now, the last part of our alignment for a 3-2-1 alignment is to define a point. We'll rotate the model. We'll click on the left side. And you notice that this is all populated here. Notice also that the probe moved through the part to get there. So that should be a quick visual cue. We say OK to our point dialog. We say OK to our base alignment dialog. If any other pop-ups show up on your screen, you can just either X them out or move them out of the way, by the way. I have minimized all mine so they won't pop up. So if you see more pop-ups than I'm getting, it's because I already went through and minimized them for the video. It does not mean that you're doing anything wrong. All right, let's come over here and let's go to our isometric view. Notice that the CAD origin has now moved from where it was before. So we had to orient the CAD model correctly. In this case, the CAD model was already oriented correctly. But once the orientation is good, that base alignment will pick whatever location is the result of filling out this base alignment window. So as you're filling out this base alignment window, that location of that gnomon may move to a different section of the part, and that's actually exactly what we want, because this is where our origin will be when we have our part on the machine. So next, remember this probe did move directly through the part when it was moving from the line to the point. So without a clearance plane, that's what would happen in the real world. Notice also the clearance plane is red, so that means we have to set it. And in this case, we'll just open it, click clearance plane from model. If I'm feeling lazy, I'll accept the default. If I'm not feeling lazy, I'll type in 100 thousandths there. Today I'm feeling lazy, so we'll just accept the defaults. Now if this ever opens up, update clearance plane settings for defined features, say no. All right, so I did steps 5 and 6 there, base alignment and clearance plane. Next, we're going to do our measurement. So we're going to go to our features tab, and the first thing we're going to do is probe our features, and we'll wait to set our strategies until afterwards. It's very tempting to do too much at once in Calypso. You'll develop your own workflow. You certainly don't have to do it the way that I'm doing it here. However, this is the way that I've found works probably the easiest. Now, one step that I didn't mention in my list here is when you're doing the base alignment, you may not pick up the strategy that you want for these first couple features. Notice that the point is green because it has already been measured, but the plane and the 2D line are gray. That means that they have measurement strategies, but they might not be exactly what you want, and they have not been measured yet. So let's double click on those while we're at it. We'll come into strategy, and here you can see there was a polyline that was measured. I don't really want to do scanning, so I'll get rid of that. Notice my point filter is already on, so I'll come over and touch 1, 2, and 3 points. Now, you can either have the simulation window open or closed when you're doing this. Just make sure you don't pause the window before you're measuring this, otherwise Calypso will freeze. Also, we can speed our simulation up a little bit. That way we don't have to wait for the graphics screen to update. I double-clicked on the 2D line here, came over to strategy. I have a line auto path that was in my defaults. We'll get rid of that. And if we move these windows out of the way, we can see our point filter is still on already. So we'll measure a point here and a point here. They're added to the list. I say OK, and I say OK to this menu as well. And now everything is green. Now Calypso is happy. Now, another thing I like to do to keep my workspace clean, I'll highlight all 3 of these features and I'll form a group. So I right-clicked and formed a group. And now you see that I can rename this, and I'll name this alignment or auto align. Right, for our automatic alignment. This is the alignment that the machine will run every single time it runs this program. All right, so now that's all organized in a group. Now we can start measuring our features. Now in this case, we'll leave the probe on for the first couple points, and we'll turn it off for the last couple points. That way you can see the difference. This probe is controlled by this measurement plan simulation window right here. So what do we need to measure? Well, we have balloons 1, 2, 3, 4, 5, 6, 7, and 8. It looks like we're measuring the overall width of the part, the width to this first step here, the second step along the x-axis, width of this third step along the y, or I'm sorry, first step along the y and second step along the y. And then we're measuring a couple of depths. So I guess I'll measure, I guess we'll measure the overall Y width first, and then this first step, then that step, then this step, then that step, then this step. A lot of times I'll try to make my programs path efficient by default. And when I say path efficient, I mean I'll pay attention to how the probe is going to move around the part. And I'm not necessarily paying attention to the numbers of the balloons because we're going to come back and revisit that later, as you'll see. So for right now, I'm just going to measure some points. So I see from my filter window down here, I am already defining points anyway. So I'll come up here and just click on the model. So I'm going to measure the overall Y width. Now, it's very tempting to come in here and set the Y width at this point. We could turn on our Y width. We could set our nominal value to whatever the print says. We could set our tolerances, and that certainly is a good way of doing this. To be honest with you, sometimes I do it this way. That's because this is a direct characteristic. So we have the option of doing this for direct characteristic. Later, you'll find that not all characteristics come directly off of the features themselves. So you can't do it directly in this window. So I'm going to show you a couple of different alternatives in this video, and you can pick the one that you like the best. So you certainly can output your characteristic at this time, and notice that because I did that, we come over to the characteristics window, and it has added that in for me. So that's kind of nice. That saves some time. Also, if I wanted to add this afterwards, I could come in here to Size, Standards, Y, and that just gives me a generic Y value. And then I could double click over here. I could go select my feature, select 0.2, say OK, set my nominals and my tolerances here. And really, I'm getting exactly the same result that I did before. It just takes quite a few more clicks, and it comes in with a different default name. So, pick your favorite, whichever one you want. For the remainder of this video, I am going to stick with just the fastest option in the interest of time. So I am still picking points here. I have a point filter on already, so I'll measure the X location of this. And while I'm here, you know what? I'll set the X. I'll set what I assume is the nominal, and I'm ultimately going to come back and check all of this information later, so I don't worry about it too much right now. But I did my nominal X value, my upper, my lower tolerance. I could actually set the name of this identifier. This is the name of the characteristic here. This is the name of the feature here. So if I was really wanted to do this to the letter of the law, I would name the feature first. So that way when I check this on, this identifier would pull the name of the feature. So that way I would have feature and characteristics would match. But I think you'll find as you get deeper into this, really the feature names don't matter so much because you can always just click on the feature on the list and it will show you what it is on the graphics screen. And you never see features unless you're in Calypso. So there's really no point in spending your time making sure all the names match. But this will become more clear as we do more complex parts. All right, so far I've done the Y overall. I've done the X position of this step. Now I'll do the Y position of this step. We'll set up the Y. We'll set up our nominals and our tolerances at this point. Again, I could just leave the nominals and tolerances alone. I could go back and do this all later through the characteristics list. It is up to you. Now notice also the position of the highlight here is relevant when you're creating features. I happened to be here when I created the last feature, so it went 0.4, then 0.2, then 0.3. Does that really matter? Well, it kind of does. It kind of does because usually we execute our programs from the feature list, meaning that it's going to execute the program in the order that you see here. So if you can create your features in a path-efficient way, that will come in by default. Of course, with all of this, we can always reorganize this later anyway. So we'll measure this right here. You know what? Let's not output the characteristic on this one, and we'll see that we can do that later. Click on our overall here. I'm not going to output that. And then we'll click over here, and I'm not going to output that. So you see how quickly you can generate your features if you're following this protocol right here. It just makes it so quick to probe the features, and then we come back and set our strategies and create characteristics later. All right, we have to do a depth for this slot, and we have to do a depth for this slot. Now, how do I know which features I should be measuring here? I pulled all this information off the print, And I have this in the back of my head and I'm using that to generate the point list. Again, I'm not too worried about it if I forget something. I can always go back and edit it later. So what is our next move? So we probed all of our features, or at least most of them. I may have forgotten some. Next, we'll set our strategies. Well, the reason we're starting with these easy files here is these are all direct characteristics, and for the most part, we're measuring either circles or points. In this case, we're measuring the entire program with points. So these points already come preloaded with their own strategy because by virtue of selecting or defining a point here, it pulls the point directly off the CAD model. So that makes that very easy. So our strategy is already done for point type features. If we had a line, a plane, a circle, depending on how you had your default strategies set, they may come in with strategies already, they may not. Even if they do come in with strategies, oftentimes you have to edit them because they're not exactly what you want for that particular application. So the next thing we're going to do is reorder this to optimize our cycle time. So let's go take a look at that. And this is really more of a nice to have than a need to have. The reason this auto align is in its own group here is because that needs to happen in the order that it happens in. So this may not be the most efficient path to measure. Maybe we could measure some other points in the line there, but really you don't know where these points are until you've aligned the part. So the automatic alignment is kind of its own thing. Again, the software calls this automatic alignment a base alignment if we want to get technical. So next, measuring point 2. Well, that's at the back of the part. Well, I just measured the top plane, the front, and then the left side. So if we're just moving clockwise, yeah, that's relatively path efficient. And we measure point 3 on that edge, then point 4 on that edge, 5, 6, 7. All right, so it looks like we already have a path efficient program. If we didn't, we could just grab any of these points and just pull them around to wherever we want. Right? I do think it comes out a little cleaner if you just make it path efficient to begin with, but hey, do whatever feels comfortable to you. So the next thing we're going to do is create characteristics. This is optional, and we can do this for direct characteristics only. So the reason I say that is we are in the Features tab. So if you want to create characteristics directly from the Features tab, they have to be direct characteristics. In other words, we could not output a distance from this X position of this first step to the X position of the second step directly from any of these characteristics. If we wanted to make a distance from, say, 0.5 to 0.3, we would have to come up here to size, distance. We would have to do a Cartesian distance, and then we'd have to come in here and select our primary feature as 0.3. We have to select our secondary feature as 0.5. And you see now that generates a distance from something to something. We can also specify a primary datum, which would be our top plane, and a secondary datum, which would be our 2D line. So that's significantly more involved. So I'm only showing this to show you what do I mean by direct characteristic. Well, direct characteristic comes directly off a feature. An indirect characteristic is what I'm showing you here. We're not worried about those in this part. Again, just want you to know the difference between direct and indirect. So this actually is not called for in the print, so we'll simply highlight that and delete it. All right, so all of these should be able to have direct characteristics. I did create some of them as I was going along. If I hadn't created them as I was going along, I could simply do so right now. Now you see this is already in here, so I'll just say OK. And I'm systematically working down the list. This one is already in here, so I'll say OK. 0.4, that's already in there. If I want to see more details, I can always hit this little arrow out, and that shows me my tolerances and the default name of the characteristic. All right, point number 5, I think this is where I got lazy about it, and I started just clicking on the model, which, again, is just fine. For point number 5, I want my x-coordinate, and I'm just assuming these nominals right now. I did happen to notice that all of the dimensions are 3-place decimals, so they're plus or minus 5. Really, we would be working back and forth with the print here. I just don't want this video to go crazy switching windows from one to the other, which is why I'm making some assumptions. You'll find that we will revisit all of this after anyway. So I'm getting my information from the graphics screen here. I see which way the arrow is pointing. I must be measuring a y-axis here, and then I'm just rounding these values and getting rid of this extra 9/10. All right, so this is going to be an x value for 0.7. This will be plus or minus 5 as well. And then this one, 0.8, this is going to be a z value. Our primary datum, z0, is on the top surface. I'm measuring the depth of this, so this is a direct characteristic that will be output as a z coordinate. All right, so we're correcting our nominals and our tolerances here. And lastly, we have this other slot, which is also 394 plus or minus 5. So we have the radius slot and then the straight slot. And there we go. So we are now done with our measurement. Right? We did our features tab. We probed the features, set our strategies. In this case, we didn't have to set strategies. They were points. We reordered them to optimize the cycle time. In this case, we ordered them in a path-efficient way to begin with, so we didn't really have to reorder, so that saved the step. And then creating characteristics. We could have done this when we were probing the features initially. In fact, I did do that for the first couple. I didn't do it for the last few, and you saw it was pretty easy to add in afterwards. Now keep in mind, you can only create characteristics from the Features tab when they are direct characteristics. Right, so all of that is just measuring off the model, and we're primarily in the Features tab for that. And now we have the Dimension Report, and the Dimension Report is really driven from the Characteristics tab. So we're going to create our characteristics. Well, we use the Features tab to do this because we had all direct features. I also showed you how we could have done that through the Characteristics menu directly, and it did take a couple more clicks. When you're doing indirect characteristics, oftentimes you have to create that from the Characteristics tab. There's just no other way to do it. All right, so the next thing we're going to do is name the characteristics. So this is one of the, probably one of my least favorite parts about doing this. When we look at point value number 2, you notice that that does highlight this on the screen. Well, what are we going to call this? I want to tie this to a balloon number. So really, that is balloon number 4. And I would say that's the y-axis overall. So I'm going to name this B4 Y overall. So to rename it, I will double-click on that. I'll highlight this, and I'll say B4 Y overall, OAL for overall. Now, all of this is already set because I already did this in my Features tab. Here is, again, where you can use your own judgment on the order that you want to do this or the process you want to use. I could have just created the features in the Features tab and done nothing with the nominals and the tolerance, and I could have updated those here, and that is perfectly fine as well. So pick whatever works for you. All right, so that was balloon 4. Now with balloon 3, I would say that's the X distance to step 1, and that is actually going to be, what would that be? That would be balloon number 1 right here, this 2-inch 992. So B1 underscore X. Step dash 1 underscore X. So that's what I would name that one. Point number 4. So this is going to be the Y location of balloon 5. So I'll name this B5 step 1 dash Y. You can name these whatever you want. This is a standard that I like to use just to make it easy to read on the dimension report. Step 1 Y. All right, so I always do balloon number and then an underscore, the name of the feature that would make sense to the person reading the dimension report, and then which axis does this have to do with? Is it X, Y, Z? Sometimes it'll be diameter, sometimes it'll be a distance. And this next one, we have the X value of step number 2, so that would be balloon number, this 3-inch 386 ties to this balloon 2, so this would be B2 underscore step 2 underscore X. B2 underscore step dash 2 underscore X. So our next feature is going to be the Y value of step 2. The Y value of step 2 would be this 2-inch 362. That's balloon 6. B6 step 2 underscore Y. And then the next one we have is the X overall location, and that is going to be balloon. The X overall is balloon 3, so B3 underscore X overall. Oh, you know what? I'm not following my own protocol here. Please forgive me for that. Yes, this can be, for me at least, this is the most challenging part of programming a CMM, is being systematic and always following the same system. But man, oh man, is that important, because the second you don't go systematically is exactly when you make a mistake or miss something. All right, so point number 8, Z value is going to be balloon number 7, and that's going to be the radius slot. So B7 underscore radius slot, and that's going to be a Z coordinate. And then this must be the last one. This must be balloon 8. So B8 straight slot. And that would also be a Z coordinate. All right, so that is probably the most painful. The most painful step is characteristics tab step 2, name characteristics. So set nominals and tolerances. Well, we already did that. We happened to do that in step 4 of the measurement tab. Keep in mind, when you're doing indirect characteristics, you might be creating the characteristics at this time. Maybe you set the nominals when you create the characteristics. You know, the order of these is up to your interpretation. All right, but one thing that I strongly recommend is step number 4, reorder your characteristics tab to match the balloon numbers on the print. Well, the balloon numbers on the print go sequentially, 1, 2, 3, 4, 5, 6, 7, 8. Right, so basically what I did here is I took the first view and I went clockwise, and then I took the second view and I guess went counterclockwise, or maybe if you think about starting at the 12 o'clock position, I went clockwise from there. So I don't really care what you do, but I want this to follow some sort of system. This system appears to be start at the 12 o'clock position, go clockwise, go to the next view, start at the 12 o'clock position, go clockwise. If you want to go counterclockwise instead of clockwise, that's fine. If you want to do the column approach and go from top to bottom, down this column, left to right, or maybe you want to go by zone and you want to go the row approach, I really don't care. Just make sure it follows some sort of system. And your blueprint or your dimension report really should tie to this blueprint to make it easy for the programmer in the future. So the reason that we named these characteristics first is now we can just pull our balloon numbers into the order that we want. So really, we're just looking at the beginning of this. B1, B2, what comes next? I guess B3, B4, B5, B6, B7, B8. All right, that looks very good. So we are now done with our dimension report. So the last thing is we're going to check our work. We're going to go to the features editor. We're going to make sure the stylus system and the stylus are set correctly. So we'll come to the measurement tab. We'll hit measurement plan editor. We'll hit the pull down here and we'll go to stylus system and stylus system. Notice that we have these blue stars on everything. That means it's the default. It's driven from a higher setting from the measurement plan itself. I have found that when you transfer these to the machines, if you have any blue stars, it will select the default on the machine. That is not what we want. So we'll come over to stylus as well, and then we'll just make sure that all of these are indeed set to stylus number 1. So if you have black text, that is good. Red text is bad. Blue text sometimes will work, but won't always work. So I guess blue text is bad as well. All right, so we made sure we have the correct stylus system and stylus. Clearance planes. We're going to make sure that our clearance plane is always along the shaft normal by default. So we can hit the pull down here and go to travel and clearance group. Notice that some of these clearance planes are not plus Z, they're plus Y. We have a plus X here, a plus X. I'm actually going to leave these alone just to show you what it means. I'm going to show you in the simulation that these clearance planes cause some very weird motion, right? So I am intentionally not fixing these just yet. Now our retract. This is an important one. This is subtle when you're watching it on the simulation, but in the real world, it's important to give yourself a little room for misalignment of the part initially. So I give myself a 1/4 inch. But then after that, if you're trying to fit in small holes or something like that, a 1/4 inch is just too big for retract distance. So 50 thousandths is a good number to use once you find the part. So think about it like this: 1/4 inch to find the part, 50 thousandths to fit in small features after that. So that is under retract distance. Now again, we got that blue text here. 1/4 inch is the default. Who knows what the default is on the CMM you're running this on? So I'll come into that and just highlight them all, and then I'll type 0.25 and press enter. So you may have to just retype that value to get it to actually take. All right, so that is for auto align. But then for the rest of the features down here, I don't want that to be 250 thousandths. I want that to be 50 thousandths. So our alignment, all these features here, anything under auto align is going to be 1/4 inch. Anything after that is going to be 50 thousandths. Right, so that way we'll get a more efficient program. It won't take as long to run, and also we can fit in smaller features. All right, and then this is an option. It turns out if you use circle paths by default, they'll use arc motion, and that just takes a while in the simulation. So for me, I like to turn that arc motion off. If you'd like to do that, that is right here under arc motion mode. You see it all starts as on. This actually runs really buttery smooth on the machine, which is a good thing, but in the simulation it takes a while, so I will just turn that off by default. Again, that one is optional. If your simulation's taking a while, I recommend using that setting. All right, so next we are going to run the simulation with collision detection on, and we want 1 click less than full speed. That's 90% speed. All right, so let's say OK to this. Remember, I did not set all these clearance groups correctly. We still have this +y and this +x and this +x, so we will see some weirdness at some points, and I just want to make that a learning point. All right, so when I say we want to run the simulation, this window has to be open. So if you've closed it while you were programming, that's fine. Just go to Planner, Measurement Plan Simulation. Bring this back over here right under your XYZ. And max out your speed and then hit the left arrow 1 time, and that'll bring you to 90% speed. The reason we want to do that is collision observation does not work at full speed. All right, so we'll come over to our Features tab, we'll hit Run. We want to do Clear Existing Results, Default PyWeb Reporting. We want to hit the pull down, and you see if we name our alignment Auto Align or Automatic Alignment or Base Alignment or whatever you want to call it, it will continually overwrite it in your system, and that will prevent you from having all of these alignments that every alignment you've ever written just simply will not be added to the list. So that's something I like to do. That is why I named my base alignment initially Auto Align. All right, so I'm going to select Auto Align. We're going to do all characteristics. We're going to run from feature list. Remember, feature list is the path efficient way to run this, right? Order of run wants to be feature list. We'll use clearance plane. Here on the simulation, we can do normal. It really doesn't matter. We can leave our speed at 300. If we want to do what we do in class, we can just type in a number there. 55 is good. I think in class we've been running 40. All right, and then we will hit start. And then we'll just watch the simulation. Now, if you want to watch this at any point, we can simply pause it and then switch it over to single step mode. I have noticed a lot of system instability when you pause the simulation outside of running the program. However, when you're running the program, it's perfectly fine to pause and then use single step. All right, now notice this weird motion of the probe. It seems like it's coming over in the y-axis extra far. Notice how it came back extra far. That is that y-axis clearance plane. All right, this one has a z-axis clearance plane. That acts how we expect. And then this one has another weird one. This is an x-axis clearance plane. So Calypso is assuming that you're using some sort of star probe here. And this one also has an x-axis clearance plane. So that gave us some pretty weird motion. Looking at how our probe points, we pretty much never want to pull off the part that way. I mean, in that specific instance, it didn't hurt anything, but it certainly was not efficient. So before we even look at our dimension report, I'm going to go back and toggle that over. We'll come to the Measurement tab. We'll go to Measurement Plan Editor. And under Clearance Group, right, so Travel, Clearance Group, we'll come here and highlight everything. And we'll set that to CP, which stands for Clearance Plane, and CP plus Z. And you notice they're all homogeneous now. This is what we want. When we're only using a straight up and down probe, they would sometimes call this a down probe or a minus Z probe. You pretty much always want your clearance plane to be Z positive. So let's rewatch this exact same simulation. We'll hit run, we'll hit start. Now pause mode was on, so now I have the ability to single step it through. All right, so there is our alignment. And now you see that all of these features are working exactly how we would expect. We are always jumping up and over in the Z-axis. Now you might be saying, hey, we didn't really need that clearance plane in between those steps. And if that's what you're thinking, well, you've probably done some CNC programming in your past, and the efficiency of the program is very important for that. And if that's the case, if you want to make that more efficient, I think it says in here somewhere, we can do sub-clearance planes, which we'll talk about later in a separate video. All right, so we ran our simulation. Our collision detection was good, and we ran that at 90% speed so that it actually worked. Let me just give you one more point about collision detection. I will, well, actually, I'll come do a sub-clearance plane right now, and we will cause Calypso to crash around this back edge, and we'll just make sure our collision detection is actually catching that. Now, you certainly don't have to do this. I'm just showing you this for an example here. Let's grab some of these points, and instead of doing clearance plane plus Z, we'll do sub-clearance plane plus Z. I will explain more detail on this later. But just with that simple one change, we come back in, we run the exact same program. This time I'm just going to let it run. Our alignment will run fine, and then we'll find that we'll crash around that back edge. So I don't know if the sound came across in the video, but it does make this cheesy sound where you're crashing into the part, and it logged each of those collisions. Right? So that is a hugely powerful feature, but again, it does not work if we delete our clearance list. It does not work if you're at full speed on that simulation. So we'll rerun the exact same simulation again. We're going to let it run at full speed, and sure, it'll run faster, but it didn't log any of those collisions. So how is that helpful? Not helpful at all. So again, I just can't emphasize enough that you want this speed slider here to be at 90%. So just click one arrow over, or mouse click a little bit to the left of full speed when you're running that. Otherwise, you're not doing collision detection at all. Again, to turn collision observation on, you just click this button. Now it's off. Now it's on. It will not work at full speed. So in my haste to show you that collision detection thing, I closed down my dimension report. So to get it back, I'll come up to View and Multiple Report. So now I am systematically going to run through this. So we'll put our dimension report on the right. We'll put our ballooned print on the left. We're just going to make sure that we have the correct, first of all, that we have every balloon and no extras. So B1 is the X step. That's good. To step 1. B2 is the step to X2. B3 is our overall. That is good. B4 is our Y overall. That's good. B5 is the distance to step 1. If we're calling this rectangular cutout step 1 and this rectangular cutout step 2, that looks good. B6 is the distance to step 2. That's good along the Y-axis. B7 is our depth to our radius slot. B8 is our depth to our straight slot. So this is looking good. Now let's check our nominals. So 2-inch 992, that looks good. Plus or minus 5. Everything's going to be plus or minus 5 on this print. Plus or minus 5, plus or minus 5. Yeah, it's all plus or minus 5, and I see all plus or minus 5s here, so that's good. So really, we just have to check our nominals. 3-inch 386 is good. 3-inch 622 is good. 3-inch 071 is good. 2-inch 598 is good. 3-inch 362, or 2-inch 362 is good. Minus 394, minus 394. So we have a good dimension report. Everything is accounted for. We have all of our features, B1 through B8. They're all named accordingly. They all have nominal values that are correct. They all have plus tolerances that are correct, and minus tolerances that are correct. So what else do we have to do here? We systematically check the dimension report. We have all balloons, nominals and tolerances are correct. And then lastly, we have details, details, details. So under our resources tab, under measurement plan comment, this is where we can pass some notes to the operator. So resources, measurement plan comment. Now, you may put some fixturing information or any other information that's pertinent to the operator running the program. So where does this come in? Well, when you go to the Run menu, you see that it comes in right here under your comment. And you might think you can edit the comment here. Well, no, you can't, because you don't want the operator to be able to modify that when they're running it by accident. So that's why it's stored under Resources. All right, so we fill out a comment. All right, and then subclearance planes, we talked a little bit about that. We'll cover it in a future video. That's optional. It's for optimization. It actually caused a crash the way that I did it here. And then we can also organize things in groups. This is really optional. It's for you a year from now. Oh, and also that's going to add groups to our features editor. So let's do that real quick. We'll cover this in a later video in more depth as well. But you see how right here I only have one group, it's auto align. But when I come to the measurement plan editor, I can see that they are organized like that. Well, really, we also have some features around the periphery. They're XY features, and then we have separately Z features. So if we come into our tab here for features, and we highlight all of our features around the outside, and we say form group, we could name this group XY features, or just XY, whatever you want to name it. And then we could rename this one. So I'm just right-clicking to rename. We can name it Z features or Z, whatever you want to call it. And now when we come into our feature plan editors, it organizes that nicely. Notice that none of that affected our dimension report at all. If we go view multiple report, everything still comes out exactly as it did before. Nothing has been modified. Well, we also have the ability to come into our characteristics list. And if we want to group these by step, let's say, let's see, how do we want to do this? So 0.4 is going to be step 1, and B1 is going to be step 1. So if we right-click and we form a group there, and we name this group step 1, and then let's go find step 2. Well, that's easy based on the way we named features. This is really just adding another level of organization to your program, and perhaps, whoops, that's supposed to be step 2, not step 1. Perhaps this is not necessary for this part. I just want to show you what that does to the dimension report. Just by doing that in our characteristics window, remember characteristics is what you care about. That is going to affect your dimension report. Now let's take a look at how this dimension report comes out. So this dimension report is now grouped by feature. So we have step 1, step 2. I would say that's not so helpful for this one because now our balloon numbers are going out of order. But there are applications where that can be very helpful, particularly if you're using a star probe and you're grouping your features by plane. So that's all I have for this video. When you submit your work, you are going to submit your inspection file. So you can just do a file, save as, and you'll save this as whatever this assignment name is. Let's go grab the name of this assignment. This assignment is offline 1100 something something direct. So we'll save it as that name. And then just put your initials at the end of that and hit save. And what I'm finding is I used to have just the inspection file, but I'm finding that that causes the CAD file to not come along for the ride. So once you save your file, I'd like you to come back in. We know that this is the one that I just saved because it has my initials at the end. And just right-click and say send to compressed zipped folder. Submit this compressed zipped folder to me along with your dimension report. So how do you print out your dimension report? You go view multiple report. Oh, it has no results available because I just saved it as a new file name. So if you want to get your results back, just go back into your run window. Maybe the report will pop up, maybe not. If the report does not pop up, then you'll go to view multiple report. In this case, it did pop up. So we'll just zoom in here a little bit. We'll click on fetch data. And we'll name this exactly the same thing as our dimension report. it will just be a PDF instead. And so we'll just paste that name in there and hit save. And when you submit this, you will submit to me this dimension report as a .pdf, and you'll submit this zip file as a .zip file. So you'll have two files attached, one PDF, one zip file. So that's all I got for this video. Thank you for watching. I'll see you at the next one.